just in time.
Test 1, 2.
Oh, that was it. Just
Yeah.
the volume. Okay, we tried that. But
Test 1, 2.
okay.
All right.
We tried that. Hold it.
No stress. All right. Have a good one.
So it's recording?
Yeah.
Okay, so let's get started. Thanks everyone for joining. So I should say a few words before we begin the defense about Nat. So I should, I first met Nat when I was at UC Berkeley, and there was this student in the class who was, it seemed to me like very advanced graduate student. So I was only half right. He was an undergrad at Berkeley. And since then, he took a detour at Perimeter and he's been here. And he's done many, many things. So I think he won't be able to cover all the different things that he's actually worked on. But one of the things that's been very satisfying, so I always think that if you're doing a PhD, ideally you should write a single author paper and get it published. So Nat has done that twice during his PhD. But of course, this usually means that you're one of these people who likes to work on their own, or is a bit off the real axis kind of person who's maybe not very collaborative. But on the other hand, Nat has many collaborations. Some of them with me, but also with people, other junior collaborators, people from different areas. Impressive thing is that he's worked with people like Matt Hastings, written papers with them on the quantum information side, and also people like Davide Gaiotto. We didn't actually have a paper with him, but I think one of his projects was inspired by discussions with him. So it's always kind of interesting to see what Nat is up to. Brought a lot of fresh perspectives to the group. And I think one of the things that I learned from his work, which was very eye-opening for me, is what exactly fractons are good for. There's a lot of interest in fractons, but I think some of the things he'll talk about today, about defining statistics for fractons, at least for me, was, it really showed the power of having these models where you can use them as a laboratory, a theoretical laboratory, to really explore fundamental concepts like quantum statistics. What are the ingredients you actually need to define quantum statistics? And the answer is sometimes surprising given what we are exposed to. So anyway, without further ado, let me turn it over to Nat.
Thank you everyone for coming to my defense today. And so today it's a great pleasure for me to talk about some work I've been doing over the past 5 years at Harvard. I was trying to think of what would be a good title that summarizes what I've done so far. And so this is the best name I've come up with. It's called Exploring Exact Dualities in Lattice Models of Topological Phases of Matter. So just to begin, let me just pull back a bit and give you a bit of a very broad picture. So our universe is quite amazing. Just from the chaos, all the chaos is going on of all the fundamental particles interacting to each other, there's somehow some emergent structure that arises out of all this messiness, from collapsing gases that forms nebula and forms stars, to the planets and crystal structures that we sort of see on Earth, or to even life itself and civilization and human interactions. So all of these are emergent structures that, like a priori, we wouldn't even think would be able to exist. But somehow it does. And maybe as a physicist, we have, yes?
Sorry, you share screen.
Oh, it's not working? Oops, sorry. Sorry, somehow I forgot to do that. that work now? I can't hear anyone, so I am assuming it's fine now.
My colleague will complain.
Okay. So I guess I was saying that as a physicist, well, I guess out of all these increasing complex structures that emerges, maybe as a physicist, we have the easier end of the stick, which is just the most fundamental of all. How does, for example, crystals emerge, or how does stuff collapse to form stars? But even though this might seem as the easiest of the problems, it's still not the easiest. And it might be even more surprising to say that all these emergent structures, we know that ultimately comes from 4 fundamental forces of nature: gravity, electromagnetism, and nuclear forces. And somehow that gives rise to rich and complex phenomena ranging from materials such as just pretty materials to sort of exotic phenomena such as superconductivity. So as a physicist, or as a condensed matter physicist, where we want to try to classify different phases of matter, so it seems like a daunting task to ask, where do we even begin? How do we figure out how many phases of matter are there that can just arise from these simple rules of 2 bodies just interacting and so emerging to some more complex structure? So one thing that is very nice that nature gave us, thankfully, is a concept called universality, namely systems with entirely different constituents can nevertheless share some very common characteristics. So for example, if you look at molecules of water, you might want to study all of these complex interactions, look at how the molecules interact. But at the end of the day, you can write down a simple phase diagram, and you might, for example, want to study the critical transition between liquid and gas. And you might do an experiment where you go to a critical point where liquid and gas, right at the critical point where liquid and gas become indistinguishable. And right at that critical point, you might see some, for example, in the experiment, you can see some sort of fogginess, some wavering pattern going on. This is called critical opalescence, where because of different length scales of things interacting, you can see some sort of, it sort of starts to scatter light at different length scales. Miraculously, this sort of phenomena, so if you try to probe correlation functions of this at this critical point, it also happens at some seemingly different and not even related system. Namely, if I put tiny magnets on a square or cubic lattice and have them interact, where they can lower their energy if their spins are aligned, you'll find that there's a critical temperature where instead of in between a phase where all the magnets try to align with each other and just pure randomness, there's a critical phase transition which happens. And this has correlation functions that exactly match that of interacting water. So it seems miraculous that for some systems, we don't even need to go to study these complex systems. What we can refer to some simple models that are defined on the lattice. And as long as we can find one representative to study these phases, we can infer a bunch of information out of such systems. So this brings me to one of the words that appear in my thesis, lattice models. And in particular, maybe, why do we want to study lattice models? So first of all, of course, many lattice models can be solved exactly. That's a very nice thing to have and gives us intuition. But second of all, even if we cannot solve them exactly, they still provide excellent approximations to realistic systems. For example, a simple model of electrons hopping on a lattice is exactly, or very similarly, describes what happens in cuprate type materials, which are candidates for high temperature superconductivity. And the third is that nowadays, in the past 10 or 20 years, we have on the experimental side in atomic physics, we can now even engineer systems that closely emulate the interactions of such lattice models. And so there are many nice properties that we can learn from lattice models, and that's what I want to talk about today. Of course, there are many ways where you can contribute to studying lattice models. But what I want to talk about today is one approach, and it is exploiting something called duality, which is another word that appears in my title. And duality, in short words, is viewing the same system in a different angle such that it can offer insights to its properties. So as a condensed matter physicist, to make an analogy, suppose I want to study a phase of matter using description A, which might be complicated. I might sort of change my point of view and look at the system in a different angle. So, and describe it using description B, for example. And by doing so, I might be able to relay that into something easier to comprehend. And moreover, in each of the descriptions, you can even tune the parameters in each side, and you can see that they can even turn into one another. So dualities offer you a very powerful tool of understanding how to relate different phases of matter to them and how to infer cool properties about them. So just to give you one explicit example, let me talk about a lattice model called the transverse field Ising model. So you might have seen this in statistical mechanics, where you have an Ising interaction given by ZZ, and you add a transverse field pointing in the x direction. And the strength of the magnetic field is given by H. And if H is 0, then you know that this forms a ferromagnet where all of the spins prefer to align either pointing all up or all down. Versus if H goes to infinity, then all the states will prefer to point to the right. That means that in the Z basis, it's a superposition of equal fluctuations of pointing up and down. Now there's a duality, a non-local duality called the Kramers-Wanye duality, that basically what you do is that you notice that you can swap this Ising term ZZ with X, and that preserves the algebra and all the commutation relations. And so by doing that, you find that after doing this transformation and rescaling by a constant factor H, you find that you obtain the exact same model, but with the magnetic field from H, it's now 1 over H. And so for this dual system, it actually has the same it's actually the same Hamiltonian, but just with different parameters. And for H equals 0, when originally it was a ferromagnet, this is now a paramagnet. And now when H is infinity, originally is a paramagnet, and this is a ferromagnet. So the Kramers-Wanye duality is a non-local duality that swaps the pictures between the two sides. And in analogy to that thing I just showed you, I have a description where on one side, it looks like a ferromagnet, on the other side looks like a paramagnet. As I rotate my picture, you actually go to a critical point where both sides of the duality, it looks exactly the same. And as you go to the other side, the roles of the ferromagnet and the paramagnet are now swapped. And so one nice thing you can infer from such a duality is that the critical point must be the point where H is equal to 1 over H, and that's exactly 1. And that's exactly sort of the midpoint where things get interesting, and you can infer properties just by setting the lattice model at this exact point. So with one example given out, let me tell you what I'm going to be talking about today in this dissertation. So what I'm going to do is I want to use dualities to relate different quantum phases of matter and try to gain insight into their properties. And second of all, I want to even search or derive new types of dualities that might have not been conceived of before, and that can be even used to theoretically discover potentially interesting new phases of matter. And lastly, it would be interesting to even implement these dualities physically. For example, if you want to do this in the lab, and towards the end, I'll comment about how that could potentially be done. So to get a bit more technical, I want to talk about what I mean by a lattice duality. And I'm going to be considering a lattice model and dualities between them. And that can be thought of as a transformation that preserves algebras of operators I'm considering in my quantum mechanical problem. And these comes into two main classes. One is local dualities, and these are dualities that preserve locality of operators. So they map local observables to local observables. And these can be implemented either by evolution of a local Hamiltonian, or if you're a quantum information, you can think of it as applying a quantum circuit. And at first you might seem that this seems boring. How could I gain insight into something that's just applying something local. But it turns out that if you take into consider symmetry, if you consider systems with symmetry, you can consider evolution by Hamiltonians or quantum circuits that need to preserve the symmetry. Then it turns out that you can use this procedure to prepare interesting phases that are protected by symmetry. And these are so-called symmetry protected topological phases, which I'll define in a moment. The second type is called non-local dualities, and local operators might be even mapped to non-local operators. And one way to think about it is that you might only have locality or unitarity if you restrict to a specific subspace of your system. And this non-localness is what gives you interesting things. If you apply non-local dualities, they can give you non-local correlations that appear in exotic phases such as topologically ordered phases, which have so-called long-range entanglement. And over the past 5 years, I have learned a lot from applying or exploiting these dualities. And here are some of the lessons I've learned. First of all, I learned how to construct interacting fermionic SPT phases. So these are fermionic phases of matter that are strongly interacting in the sense that they don't have they cannot be described by conventional band theory we learned in solid state physics. I learned how to compare lattice models with field theoretical descriptions or formal classifications. And even in some scenarios, we saw some discrepancy in the formal classification versus the lattice model description or lattice model construction of such phases. Moreover, local dualities might be interesting as a way to prepare resource states for quantum computation, measurement-based quantum computation. And lastly, local dualities can even give you insight into transitions between symmetry-protected topological phases and relate them to unconventional critical points. Of course, I don't have time to talk about all of this. So today I'll only be talking about one of the stories on the side of local dualities. On the side of non-local dualities, I explored a lot about exotic phases known as fracton phases. And using non-local dualities, one can search for new fracton phases. One can even design non-local dualities that map fermion degrees of freedom to bosonic degrees of freedom in higher dimensions. And one can even find a hybrid between conventional topological phases and these exotic fracton phases. And today I'll be mentioning these two works. And lastly, it's miraculous that turns out that local and non-local dualities can actually be related with one simple extra ingredient, which is measurement. And this is based on this very recent work we just put up. And I'll be talking about this topic as well to end my defense. So these are the summary of the topics. So let me just dive straight into the first topic, which is SPT transitions and how they related to unconventional quantum critical points. So to set the stage, let me just quickly recap what is the symmetry protected topological phase. These are gap phases of matter that have no topological order. And what that means is that the ground state of an SPT phase can be adiabatically connected to a product state which has no entanglement. Of course, because we have the word symmetry, it means that we also have a symmetry group G that's acting on our phase, and our phase has a ground state that is a unique ground state that is invariant under the symmetry G. And of course, it's non-trivial in the sense that in the presence of symmetry, it's impossible to connect a non-trivial SPT phase to the product state if there is a symmetry present. So one of the classical examples of an SPT phase is the so-called 1D cluster state or Haldane phase, where the Hamiltonian is a simple product of commuting terms. So on the spin chain, there are commuting terms consisting of poly Z, poly X, and poly Z, and all these terms commute. And the ground state of this Hamiltonian is protected by two symmetries, two sort of Ising-like symmetries, where you only flip the spins on the red sides or the blue sides separately. Now, if you have a closed spin chain, then it turns out that this Hamiltonian, because all the terms commute, has a unique ground state. But if you open up and consider a model with a boundary, then you find that there's a degeneracy a twofold degeneracy on each edge that is protected by the symmetry, and you cannot lift this without breaking the symmetry. And hence, this gives you, it shows you that you cannot connect this to a trivial product state with no entanglement. And that's why it's a non-trivial SPT phase. For people in quantum information, you might already know that cluster states can be easily prepared by acting with a certain quantum circuit. This is called the control Z gate. And a control Z gate is defined as giving a minus sign to when both spins are simultaneously pointing down. And so if you apply this circuit, you find that the Hamiltonian goes from the trivial paramagnet to the SPT. But maybe something that's less well known is that in this unitary, which acts as a local duality relating trivial and SPT phase, can actually be implemented continuously. So it's instead of a discrete duality, you can implement this continuously as long as you temporarily break the symmetry. So it turns out that this unitary, which actually can be implemented as a evolution of a local Hamiltonian, and this local Hamiltonian is no other than the Ising Hamiltonian. And for reasons that will become clear, I'm going to call this local Hamiltonian I'm going to use to evolve the system a pivot Hamiltonian. And the picture is, you can think of it as a pivot where you start from the trivial phase, you evolve by a certain time pi, and you can think of it as rotating the system by an angle pi to go from the trivial state to the SPT phase. And so that's a way to implement the duality. And you can say that such a pivot Hamiltonian generates entanglement because evolving with this Hamiltonian, you're starting with a system with no entanglement to some system with entanglement. But moreover, some of these pivots have a very nice property, which is that in addition to generating entanglement, they can also generate symmetry. So suppose I interpolate between trivial and SPT phase, and this is the Hamiltonian describing the midpoint. This midpoint automatically has a Z2 symmetry coming from the local duality, and that's because they're just swapping trivial and SPT phases. And so it has an additional Z2 symmetry. But in some cases, one finds that this symmetry is even enlarged into a full U1 symmetry generated by this continuous transformation given by the pivot Hamiltonian. And that's condition that this pivot commutes with H0 plus H SPT. And so oftentimes this midpoint describes a phase transition between trivial and SPT. And therefore this extra symmetry you find here can help you learn a lot about this local duality, can help you learn a lot about what happens at the phase transition between trivial and SPT phases. The reason we want to study this is because although SPT transitions have been well studied in one dimension by using techniques of conformal field theory, there's not a lot of progress made in higher dimensions. So for example, in two spatial dimensions, if you try to interpolate between the trivial and SPT phase, what you often find is that there's either a first order transition intervening, or either an intermediate phase that prevents you from studying a direct transition between trivial and SPT. Oh, sorry, I guess I forgot to say one point, is that since this continuous symmetry does not act on site, one can show that there is no basis for which you can make both the U1 symmetry and the G symmetry both on site. And that's because if you were able to make the U1 symmetry on site, then you know that that's impossible because a single site evolution can never generate entanglement. And yet we know that this U1 evolution will generate some entanglement because it prepares an SPT phase. And so there's no basis on which U1 and G can be both on site. And that's a condition of what people call there's a mutual anomaly, maybe in the higher energy literature. So why do we want that? This U1 times G anomaly means that either you have to break the U1 symmetry, or at least you have to break the G symmetry. So if you can find such anomaly, that might help us fine tune to a multi-critical point where you can have a gapless and direct transition between trivial and SPT phase. And to study that explicitly, we did an example in 2D where we went up one higher dimension, and instead of a cluster state, we consider a generalization called a hypergraph state. So consider a triangle lattice, and the state we prepare, instead of using control Z, it's something called control Z, where so on every triangle, whenever there's a minus sign, whenever all spins are pointing down, this local duality assigns a minus sign. And so you can prepare this so-called hypergraph state on the triangular lattice. And this hypergraph state is an SPT protected by 3 symmetries, where you can flip spins on either the red, green, blue sub-lattices of your triangular lattice as shown here. And amazingly, this unitary or local duality can be prepared continuously also by the so-called following pivot Hamiltonian. And this pivot Hamiltonian is a 3-body interaction, ZZZ, plus ZZZ for up triangles and minus ZZZ for down triangles. And it turns out that if you evolve by this pivot Hamiltonian for time pi, that exactly prepares you the hypergraph state. And this pivot Hamiltonian satisfies the 2 criteria I gave you, which is that it generates entanglement, as you just said, but moreover, at the midpoint between trivial and SPT phase, there's an exact U1 symmetry generated by this pivot Hamiltonian. So what do we want to study? We want to study a direct transition between trivial and SPT. So you can naively, you can just do an interpolation between trivial and SPT. And these people have studied it and found that unfortunately, there is an intermediate phase blocking a direct transition between trivial and SPT. And this is given by a ferromagnet, which spontaneously breaks all these Z2 symmetries. So in each sublattice, you have an Ising ferromagnet. So to study and try to tune to a phase transition, what we did was we added an extra term, which is an anti-ferromagnetic Ising coupling, anti-ferromagnets, so that we want to suppress this ferromagnetic phase and try to sort of get rid of it. And note that this extra term we add commutes with both the symmetry of the system and the pivot symmetry. And so it preserves the anomaly if you are exactly at this midpoint. And so what I did was I did some quantum Monte Carlo simulations to study the phase diagram, and this is what happens. So the original study was for j equals 0, in which you find a direct transition. But as you tune j upwards, you find that there is a multi-critical point where beyond that, this pivot symmetry is spontaneously broken. But there is exactly at this multi-critical point, you find that there is a direct transition between trivial and SPT, and that can only happen between these 2 phases where on one side the pivot is broken, and here the symmetry G is broken. And so by fine tuning, we are able to find a direct transition between these 2 phases. And let me mention before I move on that there's an interesting connection to so-called deconfined quantum critical points, which are exotic critical points which happen in a totally different scenario, which is 2D quantum magnets. And so I won't go into details how this correspondent works, but you can think of the symmetry breaking phase as corresponding to the nail phase of the nail VBS transition in a deconfined quantum critical point. And the part where you have a first order transition can be thought of as the VBS phase, where you form dimers in a particular pattern, which breaks a certain C4 rotation on the square lattice. And this C4 rotation is realized in the continuum as a U1 symmetry, and that's the analogy of this pivot Hamiltonian. Of course, you can perturb to either side of the phase diagram using the monopole operator of the DQCP, and that corresponds to breaking this U1 or C4 rotation down to a Z2 subgroup. And that corresponds in the nail VBS picture to squeezing the lattice so that you prefer, for example, bonds forming on the x-axis over the y-axis. And the trivial and SPT phases can just be thought as the 2 preferred dimerizations on this sublattice. Okay, so
So Subir, you have a question?
Hello, can you hear me?
Yeah, I can hear you. I can connect.
Yeah. So I think you may have answered it. My question was, what is the operator that corresponding to the horizontal direction between that takes you from the U1 spin liquid to the U1
Right, that's just the
superfluid
monopole operator.
to the monopole operator takes you to an SPT phase. Is that right?
Mhm.
Just the simple monopole. I see. Okay, thank you.
Okay, so let me move on to the next topic, is mapping fermions to bosons in higher dimensions. And so in 1D, I mentioned this famous Kramers-Wanier duality, but there is also another interesting duality in 1D, the so-called Jordan-Wigner duality. And in this duality, instead of mapping spin chains to spin chains, you're actually mapping fermions on a lattice explicitly to spins on a lattice. And there's a very similar phase diagram that happens. So instead of having an Ising model, Ising interaction, I now have a hopping term for my Hamiltonian, which I'm just representing with Majorana fermions. And I have, instead of the transverse field, I have the local fermion parity of each fermion. And there's a simple phase diagram. So when H is equal to infinity, this term is preferred, and you just have an atomic insulator where everything is just in the trivial Fock state of your fermionic space. And that's sort of the analog of the paramagnet with no entanglement. And whereas if the hopping term dominates, then you enter the so-called Kitaev phase, where at the edge you find some Majorana edge modes, and that's sort of the analogy of the degeneracy of the ferromagnet in the bosonic case. And so there have been previous attempts to generalize both the Kramers-Wanier duality and Jordan-Wigner duality to higher dimensions. The higher dimensional one of Kramers-Wanier has been worked out maybe 20 or 30 years ago by Vector and Kogut-Kitaev, whereas the famous duality where you can map an Ising model to a Z2 gauge theory. And that's the famous mapping of obtaining the torque code Hamiltonian. However, there have also been attempts to do this for so-called higher form symmetries or subsystem symmetries. And these are more exotic symmetries that do not act on the whole spatial manifold, but they only act on a subspace or submanifold. And these submanifolds can be subdimensional, or they can even be some exotic fractal, for example. Surprisingly, the Jordan-Wigner duality to higher dimensions has only been proposed within the last 5 years by these folks. And what I want to do is complete the picture and show that you can also do that for higher form symmetry and subsystem symmetry as well. But of course, you can ask, why do we want to even study in the first place? So let me give you some context. So let us step back a bit and let me talk about something that might seem unrelated at first. Let's consider a fermionic system where usually we think of a kinetic term as a two-body hopping on a lattice. But let's say the two-body hopping is disallowed, and the only possible correlated hopping that is allowed is this four-body operator, meaning you can only create or annihilate 4 fermions at a time. So for example, from the vacuum, I can create this configuration of 4 fermions. But now you notice that suppose I want to move this fermion, then I cannot really move it, because usually if I have a two-body operator, then I can just hop it to the other side on the right. But once I try to hop this, I'm creating other excitations, which is energetically unfavorable. So we find that with only such type of hopping, such an isolated excitation is immobile. And that's what people in the community have been calling a fracton excitation. What's more interesting is that since we were considering fermions, these fractons are somehow also fermions, which might seem surprising to you at first, because when we say something is a fermion, usually we think of spin statistics, where if I exchange 2 fermion particles, I will get a wave function that is a minus sign. Nevertheless, these are fractonic particles, they can't move. So how do we even exchange them? That seems like a very mysterious thing. It turns out that for one way to think about these excitations as being fermions is that they cannot be condensed. So suppose you try to proliferate these fermions. For example, let's try creating 4 of them on this plaquette, acting with the hopping operator on the next plaquette, and then annihilating back. You find that this process gives you a minus sign. So because of some weird statistics going on, even these particles cannot move, you find that you cannot proliferate these excitations, and so they cannot be condensed. So in some sense, there is some fermionness going on to these particles, even though they cannot move. So the reason I want to study these dualities is because now you can map a fermionic system, which such a property, to a spin system, which has no fermions, but nevertheless, because of the excitations that happen in the spin system, you can realize a bosonic phase where emergent excitations are fermions. And nevertheless, these emergent excitations are even immobile. So that constitutes finding a new phase of matter that people haven't considered before. So just to review how the Kramers-Wanier duality works in 2D, it's very similar to 1D. So what happens is that you have the 2D Ising model with Ising operators and the transverse field. And what you need to do is you just need to map each poly X operator to a product of poly Z's on each edge, surrounding edge. And for each Ising term, you just map it to a transverse field living on each edge. And the following mapping works well on algebras, but if you consider the states of the Hilbert space, this operator doesn't work on the full Hilbert space, and that's why it's a non-local duality. So there are certain constraints where you have to be in the correct subspace in order to map properly. For example, you notice that all of these vertex operators, if I product over the whole lattice, just cancels to the identity. And that gives you a constraint on that the product of all poly X terms is an identity. And that's just the Z2 symmetry of the 2D Ising model. But similarly, if I take all the Ising terms and product, that gives me the identity, that maps to a plaquette term of X on my dual model. And for people familiar with this plaquette term and vertex term, this is just the torque code Hamiltonian. And so you can say that the paramagnet maps to the deconfined phase of the Z2 gauge theory, which is a torque code, and the ferromagnet maps to a confined phase. Now, we can just replicate this mapping or this formula for fermions. I just need to replace a poly X with a fermion parity operator. And instead of having an Ising operator, I just need Majoranas, which act as a hopping operator for my fermions. And so you find that instead of getting a dual Ising model, where you have some product Z terms and the transverse field X, now these transverse fields, to satisfy the algebra of fermions, which may not commute, you need to attach certain poly Z operators. And so you get an Ising model, nevertheless, but with non-commuting transverse fields. And so by using such a duality, you can realize new deconfined phases of matter just by mapping fermions to bosons. And so here's the general recipe. Pick your favorite generalized Ising model, and you just need to replace poly X with fermion parity and Z with either one of these Majoranas. And you'll get a fermionic model with generalized hopping terms, but after you do the Jordan-Wigner duality, you will find a new type. You might find a new type of stabilizer code or phase of matter in a topological phase. And the distinction is that when one of these excitations is a boson, the excitation here, despite in the spin system, will be fermionic. And so you might wonder whether this duality actually exists. But in this paper, I proved that given any translation invariant fermionic algebra generated by an on-site fermion parity and any of your favorite correlated hopping operators for fermions, one can always find a dual Pauli algebra, which is given by an Ising model with possibly non-commuting transverse fields. Moreover, in addition to the existence, this dual model is also constructive, so one can always write down explicitly, algorithmically, a formula for that. And this is unique up to a finite depth circuit you can apply to your phase. And moreover, as I show that there are some constraints on the symmetry, the operators that product to the identity to show, you can show that there are exactly one-to-one correspondence with the dual symmetries. And I won't go into the details of how this is proven, but the basic idea is that you can rewrite all of these operators as using a polynomial representation of Majorana and Pauli operators. You just need to denote the positions of where the Pauli operators are. And in short words, you find that this non-local duality in the most sort of mathematical way to phrase it, it is just a commuting diagram. So you can find that you can always find a dual model as long as you can make a diagram commute. So that maybe that's a very math way to say it, but it's a very nice result. And so once we have this machinery, we just need to turn the crank and just try everything we have in an arsenal. And let me just go through one particular example with so-called related to the X-cube model, which has fracton phases. So let's consider fermions, and where I only have a ring exchange type hopping, as I mentioned, there you can only hop 4 fermions at a time on a cubic lattice. And you find that the fermion parity operator can be mapped to a dual lattice where you have poly z's on all the 12 edges of the cubic lattice. And this hopping operator becomes a transverse field poly x, but attached with extra z operators as shown. And instead of getting the usual x cube model, which is a fracton phase, where the stabilizers are given by this cube term, and usually you have only these 4 red vertex terms, now they're decorated with extra poly z operators to guarantee that an excitation of this cube, a violation of this cube, will always have fermionic statistics. And so you can play this game with other weird models. For example, you can even do this for a fractal spin liquid, where particles can only live on some weird fractal pattern as shown here. And you find that suppose you create 4 fermions at a time in each tetrahedron, and you do this process, you'll get a minus sign. And so this minus sign also, in some sense, tells you that you cannot condense these particles and their fermions. Okay, so let me now move to my third topic, which is, I guess I should mention also that this project just started during the pandemic where everything was hybrid. So to be trendy, we started thinking about what can be something hybrid we can work on. And this turns out to be a hybrid between conventional topological phases and fracton phases. So what is hybrid? The 2 constituents are usual topological orders, such as a Z2 gauge theory in 3 dimensions, such as the 3D toric code, where the charge is a point particle and the flux is a loop object. And the charge, when you move it around the flux loop, you gain an Aronoff-Bohm phase of -1. On the other hand, the X-cube model that I just mentioned is sort of weirder. It has fracton excitations, that is, you have charged particles that cannot move at all, and you have magnetic or flux particles that can only move in a 1D line, and they're so-called line-ons. And so far, people have just been treating these two as sort of different, just put them in different buckets, and let's not care about how, there's not a clear relation of how these 2 models are related. And you might ask the question, maybe they're just 2 separate families. But in this work, we show that no, they're actually not separate. And we can even come up with a model where it's not a tensor product between a usual topological phase and an a fracton phase, but they actually can coexist. And so what happens in this weird model is that if you take 2 fractons which has no mobility and fuse them together, you will actually get a mobile particle of the 3D toric code. And reciprocally, if you took 2 loops of the 3D toric code and fuse them together, you will get 4 line-on particles of the X-cube model. And so there's some weird interplay between fusion and braiding between these 2 models. I won't go into the details of this exact model, but what I want to like to offer is some intuition to how this works in a somewhat simpler model, and you'll see how that generalizes easily to the X-cube case. So let's consider a stack of clock model. So let me consider a Z4 clock model, which is a generalization of the Z2 Ising model, just a Z4 version of it. And instead of having poly operators, which anti-commute, now it's a 4th root of unity. So there's a phase I. And now I'm considering a 2D stack of them. So I can have my transverse field, and I can consider Ising or clock term, which sort of hop charges along in each 2D plane. And so if we start with such a Hamiltonian, it initially has a Z4 symmetry, which is a Z4 symmetry given by this X operator for every plane. However, now let's consider adding a tunneling term, which hops only charge two operators in the z direction. So I don't allow charge 1 to hop, but I allow charge 2 to hop in the z direction. So what happens to the symmetry now is that in each plane, there's no longer a z4 conservation. There's only a z2 conservation left because charge 2 particles can tunnel. However, globally, there's still a global z4 symmetry because overall in the 3D system, you're still conserving z4 charge overall. And so this is a very weird symmetry in which you have an interplay of subdimensional symmetries, namely the z2 in each layer and the global z4. And namely, if you product all the z2 symmetries in each layer, that gives you a global symmetry, which is a subgroup of the global z4 symmetry. So it's not separate symmetries, they're actually embedded into one another and interacting in an interesting way. And you can see that some of the charges here have restricted mobility. These charge 1s can only move in the plane, and while the charge 2 can move freely in 3 dimensions. And so with this weird symmetry, what you can do now is you can gauge the remaining symmetry. And that's what I mean by forming a non-local duality. And this new non-local duality we apply gives us a way to realize this weird phenomenology of topological orders with mixed properties between usual topological phases and fracton phases. And for people who are familiar with condensation, let me offer a complementary view, which is that instead of adding charge 2 hopping and then gauging, what you can do alternatively is you first gauge the Z4 in each layer, then you get a Z4 gauge theory or a Z4 toric code in each plane. Then what you can do is the equivalent of this charge 2 hopping is that you can condense pairs of electric charges E square, and then you will also arrive in this hybrid toric code phase. So this non-local duality actually gives you an exactly solvable model, which looks very similar to the 2D and 3D toric codes, but they're mixed in this interesting way. So if you just squint and look at the top row, this sort of looks just like the 3D toric code, and the bottom just looks like a stack of a 2D toric code. But the weird property of the model is that the vertex term of the 3D toric code will square to the vertex term of the 2D toric code, and the flux term of the 2D toric code, plaquette term, will square to one of the plaquette terms of the 3D toric code. And if you work out what the excitations do, they'll actually do exactly what I told you, is that two charges with restricted mobility can fuse into a charged particle with full mobility, and the flux loops can fuse into a bunch of, will violate only these plaquette terms in 2D, which now have restricted mobility. And you can even work out the braiding, and you find that a flux loop going around a particle restricted mobility can give you a phase of I. And so this is the story for when you have a subdimensional symmetry in sort of one foliation of your 3D space. But of course, you can readily generalize that to other cases. For example, to recover the X cube model, hybrid X cube I just told you about, you can just gauge, you can consider more planar symmetries or more foliations, and you will readily get this hybrid X cube model. And moreover, by choosing fractal symmetries, you can even get a hybrid model between a usual topological order and a fracton order with sort of fractal-like statistics with, fractal-like mobility and weird sort of fusion and statistics. The second generalization is you can go beyond the groups I just told you and go to any finite group. So throw me a finite group and an abelian normal subgroup, and I will give you a hybrid fracton model that hybridizes between a fracton theory with gauge group N and a gauge theory or a toric code with gauge group Q. And this hybrid fracton order can be realized by just following that recipe. You start with a paramagnet with a G global symmetry and N subsystem symmetry, where the subdimensional symmetry, of course, you have to pick what type of subsystem symmetry you need for your model. But after you do this, you can then use a non-local duality to gauge the symmetry and prepare a whole family of models. And the model I told you just previously was the case where G is equal to Z4 and N is Z2. But if you pick G to be non-abelian, you can even prepare these hybrid fracton orders where where charges since they're non-abelian, they become non-abelian fracton excitations, namely they're non-abelian particles that have restricted mobility. And so we presented a family of models which hybridize between a conventional topological phase and a fracton phase. And you can think of it as a generalization of the quantum double model to an arbitrary fracton phase. Yes. Yeah, so n has to be abelian. That's a good point, because we don't know how to start with a system with non-abelian subsystem symmetry, and the reason is the following. Suppose we choose we have different planar subsystem symmetry. So actually, it's fine if you only have one foliation, for example. But if you start to have more foliations, then you can compute some commutator, and you find that it has a lower subdimensional symmetry. And then you reduce it further, you find that there's a local symmetry, but that doesn't really work. So you can't have non-abelian symmetries that only act on a lower dimensional plane if it's proven. Layer is fine, and you can do it for even n non-abelian, and we constructed a model for that. Yeah. So it also has this hybrid phenomenology, just as this, and you can do that for a general quantum double model. And the idea is you start with a quantum double model of G, and you just condense particles that you want to make mobile, and that's basically the construction. So you can choose which particles you want to make mobile, and that corresponds to choosing different subgroups of n. So in the last few minutes, let me mention about how we can actually relate local dualities and non-local dualities by adding an extra ingredient, which is called measurement. And so recently there has been some exciting work that's been going on experimentally, both at, for example, Harvard and Google, where you can actually prepare a non-trivial topological ordered state, such as a Z2 spin liquid or this so-called Z2 toric code. One question, though, is that when you want to prepare non-local dualities, you need to, for example, from going from a trivial phase to a spin liquid phase, you need to tune adiabatically through a phase transition, meaning that the larger the system size, the longer it takes to prepare. Similarly, on the quantum circuit side, it means that your circuit depth must scale with the system size, and actually it's been proven that you actually need linear depth circuits. So it seems that all such preparations are not scalable in the sense that the larger the system size, the longer you have to take to prepare. But actually, it's been realized that by these folks about 20 years ago, that there is a sort of cheat you can do, is that you can use measurements to prepare long range entanglement by just using a short range entangled state and performing measurements. And the idea is, let's start with a product state and let me prepare a cluster state. This can be prepared in a finite time using a finite depth circuit or some Ising evolution. And the state satisfies ZXZ equals to 1 on this lattice. And now what you have to do is let us measure the red sites in the X spaces. And so this sets the eigenvalue of X equals to plus minus 1. And so you find that the blue sites now satisfy ZZ equals to plus minus 1. And so if the outcome is plus, then the spins are aligned. But if the red side is a minus, then the spins are anti-aligned. So this is almost a GHZ state. And what you only need to do is now you need to just, depending on the measurement outcome, you just need to rotate your states, for example, so you can apply some X rotation to make all the states, blue states pointing up. And now once you forget the red states, you successfully prepared a GHZ state. A more general framework we found, though, to view this is actually that the cluster state preparation I just mentioned is only about a special case of a more general picture, which is performing gauging. Namely, if we use the cluster state entangler, and let's fix the measurement outcome to be the plus state on all the red sides, then actually this is exactly implementing the Kramers-Wanye duality, which maps X to ZZ. So by measuring a local duality, you can obtain a non-local duality. which can give you a quick way to prepare long-range entangled states. So why is that the case? Because let's consider a poly X operator. Once I push it through this cluster state entangler, I'll get the stabilizer ZXZ. But if the outcome is just plus, then I can just absorb this into the plus state because the eigenstate is 1. And then I'll get ZZ. So I've shown that X will be mapped to ZZ, and that's exactly the Kramers-Wanye duality. Now, even if you have to measure and you find different outcomes, that's not a problem because you can easily fix this by rotating appropriate sites using your knowledge of the measurement outcome to exactly perform Kramers-Wanye duality. So you can perform a non-local duality even without post-selection by just using some feed-forward mechanism by knowing the measurement outcome, you can fix correspondingly the states you want. And so with this general framework, it gives an insight into how non-local dualities or gauging can be implemented in any input state. And the previous studies, previous stuff that people have to study is but a special case where the input is a product state. So this has, there's a nice to note that there's a very similar picture you can note with quantum teleportation, but where you perform entangling and measurement, and that teleports the state from one qubit to the next. Here, we also perform entangling and measurement, but instead of performing identity, which does teleportation, it gives you something more. It does a non-local duality. And so perhaps in high energy terms, if you prefer to think about it this way, you can think of this cluster state entangler or evolution as performing minimal coupling, and the measurement is just performing gauge fixing. So that gives you a physical way of interpreting what this non-local duality or unitary plus measurement is. And this is just why it's performing gauging. So as an example of this generalization, instead of just gauging the fixed point paramagnet, you can actually gauge any point in the phase using unitary plus measurements. And that prepares you a ferromagnet of which the GHZ is but a special case. And by gauging the 2D paramagnet, you'll get a deconfined Z2 gauge theory of which the toric code is but a special case. And so this vastly generalized what people have proposed what can be done, where instead of just measuring cluster states or sort of measuring stabilizers of your code, what we can do now is that you can even measure general SPT phases, which corresponds to measuring non-stabilizer codes, and you can get other exotic phases of matter such as twisted quantum doubles. And all these weird models I propose, hybrid fractons, fractons that are fermions, all of these can be prepared in the scheme where you have multiple rounds of unitary evolution and measurements. So all the weird models I propose can actually potentially be physically realized in the lab one day, hopefully. And so just to give you some examples, you can instead, you can prepare non-stabilizer states, such as first doing a product state, and by a mix of local and non-local dualities, you can prepare all these exotic states. For example, using a local duality, I can prepare an SPT phase, after which I can perform a Kramers-Wanye duality, which is applying the cluster state entangler and performing measurements. And that gives me, for example, double semi on topological order. And as a second example, you can even prepare non-abelian topological orders, which can't be prepared by measuring usual cluster states. Namely, you start from a product state, apply the Kramers-Wanye duality to, for example, prepare a Z3 toric code. Then you can apply a local duality to prepare a symmetry enriched topological phase. And that is a Z3 toric code, which you now have a Z2 symmetry, which performs charge conjugation. Then by gauging this charge conjugation symmetry, using a different duality, that's sort of like measuring this SET phase, you can then prepare non-abelian topological orders such as S3. And let me also mention that the Jordan-Wigner dualities I talked about can be similarly prepared by considering the fermionic variant of cluster states. You just need an appropriate SPT protected fermionic symmetries, and that will converge between fermionic and bosonic degrees of freedom for you. And lastly, fractons can also be obtained by gauging subsystem symmetry protected topological phases. So to summarize, what I've talked about today is how what we can learn from dualities in lattice models, and in particular, how local dualities can give us insight into transitions of between trivial and SPT phase and relations to more exotic quantum critical points. For non-local dualities, I've shown you how to construct new dualities that can even realize new phases of matter that haven't been proposed before. And lastly, these two dualities have a nice interrelation where you can turn a local duality into a non-local duality just by performing measurements. Okay, so let me now move on to the acknowledgements. Oh, should I go to questions first, or? So I guess one thing that's interesting, I guess that was one of my backup slides, but so for example, to prepare the Tor code, there's actually a way you can potentially prepare this in experiment using Rydberg atoms. And one way to do this is to have two species of Rydberg atoms, where, for example, you can load an optical trap with cesium and rubidium. And one nice thing of having this sort of two species is that you can readily measure one subspecies. And what that does is when you prepare a cluster state, for example, on the square lattice, by measuring all the blue sites, you can prepare a toric code state. So what you need to do is you only need to initialize in the 0 state, perform Hadamard, then evolve with this many body Hamiltonian, which is the Ising Hamiltonian, to perform a local duality, which I mentioned prepares an SPT phase. Then the non-local duality is then achieved by measuring the red sites, and then you only need to fix the blue sites depending on measurement outcomes. Of course, one doesn't not necessarily need a Rydberg, dual species Rydbergs. One can also do single species Rydbergs if one can potentially shuttle atoms around and entangle them, for example, one of the recent papers in Misha's group. Or one can even do it in quantum devices that are not Rydberg atoms, such as superconducting qubits. As long as you have some quantum computer that can entangle gaze, these proposals can be done. So should I stop for questions now, or should I do the acknowledgements first? Okay.
Oh, can I ask questions? Or...
So it is a great pleasure to have worked with Ashwin. As Ashwin mentioned, I met him in 2016 when I was taking his StatMech class at Berkeley. And back then, actually, I was working on astrophysics. And I was actually just got accepted to Harvard, but I wasn't sure what to do for my PhD. And back then, I was asking Ashwin whether I should come directly to Harvard. And Ashwin said that actually I should do a master's program at Perimeter Institute first for 1 year to sort of figure out what I wanted to do. And after 1 year, I realized that I wanted to do condensed matter physics. And then I came back to Ashwin at Harvard and said I wanted to work with him, and he graciously took me as a student. It was only then that after starting to work with him, that I realized that when I was back in Berkeley, people often called him as one of the stars at the physics department, and I just came to understand why, because of his breadth from very abstract theoretical work to relation to, for example, recent experiments. And Ashwin has always had, impressed me by his quickness to digest new concepts whenever we talk about something new. And also, I was always impressed because everyone in the group seems to be working on multiple projects, from graphene to dynamics to topological phases. And the fact that he can juggle between all these different stuff very seamlessly seems like magic to me. Moreover, Ashwin has been a very caring advisor and has always given me opportunities from connecting me to people that have the same interests as me outside of Harvard, for example, or to even mundane stuff outside research, such as looking over at a presentation slide and giving me feedback. And also, most importantly, I have been very grateful for the academic freedom that he has given me and encouragement he has given me throughout my PhD. And I hope that in the future I can, this has sort of given me some inspiration to take Ashwin as a role model in the future if I ever have students of my own. I would like to also thank the two committee members, Subir and Misha, for serving on the committee. And Subir has taught one of the best classes I took at Harvard on quantum phases of matter when I was a first year. I must admit that maybe back then I was too young and naive, but looking back at the notes now, I realized that these are one of the best lectures he has given. And also because this semester I'm a TF for Ashwin class for 295B, his resources that he taught last year has been, which are on YouTube, have been very, very critical for my preparation for classes as well. And of course, Misha is a powerhouse in the department, so to speak. And of course, the recent experiments on spin liquids that it was done in collaboration with Ashwin and Ruben has inspired me to think more about safe preparation of topological phases, which is the last topic I presented today. In addition to thanking the three committee members, I would also like to thank these Davide Gaiotto and Chenjie Wang, who were my supervisor and mentors back when I was doing my master's at the Perimeter Institute. And they sort of taught me a lot from topological phases to sort of view topological phases from multiple views, from the high energy view to condensed matter view. And they have sparked my interest while I was searching what I wanted to do. And that's how I sort of ended up working in this field today. So I wanted to thank them for that. Moreover, I wanted to thank all my collaborators over the past 5 or 6 years, starting from TI, where I work with Chenjie Wang and Meng Cheng on fermionic SPT phases. Also, Lucas, Zhongwan, and Matt for some work on the generalized double semion model and comparing field theory or classification of topological phases to lattice models. In the middle row, I also want to thank Ruben and Ryan for working on the pivot project and also these measurement projects, Sargar and Wenjia for working on hybrid fractal models. And it was these folks that sort of kept me going during the pandemic when I was sort of back in Thailand and in the different time zones. So I would like to thank all these people for talking to me during that time. And then the bottom row, I would like to thank Yuan and Tyler, which we met at March meeting here in Boston in 2019. And we have been great friends ever since when we have many projects going on together. And more recently, we have joined forces with Arpit, Wilbur, and Dom to work on more quantum information aspects of topological stabilizer codes and relations to quantum cellular automata. So in addition to these folks, I'd like to also thank everyone in Ashwin's group for teaching me many stuff and for hanging out. Here's one of the photos during the Christmas party this year where we are pledging our alliance to Team V. I would like to thank also Ruihua and Shang for being my housemates, and Saran, who I apologize for not having Saran, but this was one photo we took during our trip to Japan for a conference. And of course, a lot of this has been online, and here is one of our failed attempts to try to use GatherTown. It ended up miserably, where if you notice, this is me that can't even connect to the internet when I was in Thailand. And yeah, we ended up just playing games and just not doing work. So we just ended up going back to Slack. But nevertheless, nothing beats the high quality GIF memes that you can have on Facebook Messenger. Here's one chat group we have with Ruben and Ryan where we have serious conversations about Hamiltonians. So in addition, I would like to thank all of my peers and mentors and physicists that I have met out of the year. There are so many people I would like to thank. You're probably somewhere in this list, hopefully, but in lieu of that, let me just share some photos that I've taken with some of you over the years. It's been great memories from summer schools to for both people inside and outside Harvard, and also my roommates and friends who are here for my defense here. And last but not least, I'd like to thank my family for their unconditional love, and without which this journey would have even be possible. Thank you.
Answer some questions.
I have one question about the last part, which actually is very good. But I sort of have a question about the implication. So the reason, for example, like preparing Tori code for this measurement is important because it's error correct, right? And at that point, you sort of don't rely anymore on any kind of protection or anything like this. Right?
Oh, right. So
you
one.
You basically wait for the user to keep measuring. You keep measuring syndromes periodically, and that way you can extract, you can do error correction.
Right.
So the question is with all of these other exotic states you prepare, right? Then there's no Hamiltonian.
Right. That's.
So in what sense are they interesting or useful? What is kind of perspective?
Right. So for people at home, the question from Misha is: once you prepare the Tora code, how for more exotic phases of matter, how do you protect it? And of course, for the Tora code, we can do active error correction to continue to measure these stabilizers. But for more exotic phases of matter, the question is, what do you do to protect them? And that's what we want to work on more. So for example, for these vertex terms, to ensure that there are no charges, one can probably measure them. But to measure, for example, these flux terms for the non-abelian phases, you probably need something more. And interestingly, it's the sort of symmetry operators that you need to measure are not are symmetries that are not described by group theory, actually. So one has to find more exotic ways of measuring that, and that's what we want to further work on.
Oh, can I ask a question? Can you hear me?
Related question to that. So there's some scheme to have multiple stages of doing doing measurement. If there's only one round, it feels like there's a sense in which even if I didn't do kind of these corrections, I still roughly get the rest state of the stages.
You mean if I don't do?
If I don't like do the correction like based on the measurement results. So I guess basically.
Oh yes. So in those cases, you'll just prepare an excited state of the Tora. So what happens if I don't post correct? Depending on the measurement outcomes, it turns out that you'll just get excited states. For example, for the Tora code, if you don't protect it, then you'll just get excited states where you have anyons. So whether the measurement outcome is just telling whether you have an anion at each vertex or not. And so since you know where the anions are, the correction is just to pair them up correctly.
Yeah. And I guess my question is, if you have these multiple rounds of measurement, are there cases in which like feeding back and actually doing the correction makes a difference?
Right. Yeah, that's a very good point that I didn't get to mention, which is for these multiple round measurements, you want to correct in every round. And the reason is because if you didn't correct it, then this anion that results as a measurement outcome, after you do the second round of measurement, it can be carried over to a non-abelian anion. And this non-abelian anion is now hard to pair it up. So you want to make sure that you get rid of all the anions in each round. And in fact, the reason that these proposals for non-abelian anions in the past have been hard to prepare in finite time is because if you gauge everything all at once, you always get non-abelian anions, which are hard to pair up. But here we show that by sequentially gauging and fixing it every round, you can always pair up non-abelian anions, which are efficient. And that's why you can do everything in finite time. Yeah, are there any questions from the Zoom folks? I might have not made the sound come out correctly, so I don't.
Can you hear me?
But
This is Subir. Can you hear me? Well, maybe. Can you hear me?
Yeah.
Yeah, I just wanted to go back to the deconfined critical point. I still don't understand how the monopole operator is both the VBS operator and the SPT operator.
So you mean what are the relevant perturbations here? So the
How come there is a monopole operator, which is also the operator that gives you VBS? Yeah, maybe explain why the single monopole operator, why the relevant perturbation.
There are two relevant perturbations here. One is the mass term, which you can tune, for example, in this direction, and the monopole operator is the one that tunes between the trivial and SPT phase. And so exactly on this line, you have a full U1 symmetry, but by perturbing with the monopole operator, you're destroying that to a subgroup, which is Z2. And so by perturbing you don't have this full U1 symmetry. And in the picture of this pivot Hamiltonian is that you're doing some rotation around the axis. I'm not sure if you see me, but so there's an exact symmetry only at the midpoint, and outside there's a Z2 symmetry that swaps trivial and SPT.
Yeah, okay, I understand why there's Z2, but why is it SPT? I mean, why is it still has some topological structure?
Right, so the analogy is that for the VBS phase, you can perturb it by sort of squishing the lattice so that the C4 rotation is broken to a C2 rotation. And now you will prefer to have dimers only on the x-axis versus the y-axis, for example. And so by doing this, by perturbing in this way, you are just squeezing the lattice, and now the C4 is reduced to C2, and the trivial and SPT are just the two dimerizations of the VBS.
Okay, thanks.
Yeah.
Yes. Forgive me for the naive question. So I don't often think about fermionic hopping models.
Mm-hmm.
So is it just kind of like a nice way, like a different way to interpret things like stabilizer codes, or is there kind of some implication that we should take away? You could realize certain types of stabilizer codes, kind of efficient modeling of these different fermionic hopping problems. Is there some sort of implication here? Or?
Yeah, so there are people who study when can I solve exactly by stabilizer codes by turning them into free fermion problems. That's one question. I'm sort of approaching this in the other way. Let's start with some weird fermion model that has some weird hopping, and then we can dualize that to a spin system which has emergent excitations with these properties. And so, well, in terms of just a phase of matter, it's already interesting to think what different types of excitations you can have and what their statistics. Of course, it still remains to be studied what the, for example, quantum computational capability of these phases are. For example, the 3D toric code, there are actually two types of 3D toric codes. One is where the charge is a boson, and one where the charge is a fermion. And superficially, they are, in that case, they're more or less the same in terms of quantum computational capabilities. But there might be different defects you can insert that might give you different logical gates if you can insert defects into your Hamiltonian, and that's where the difference comes in. But that remains to be studied for these new models that I talked about today.
Questions?